Hey everybody, it's Tony from Adafruit, and I wanted to talk a little bit about the I2C protocol. So I've been playing with some devices like some analog to digital converters, and they use I2C to communicate with the Raspberry Pi. And I thought it'd be interesting to do kind of a deep dive and look at what the I2C protocol looks like and how to use it in a Python program, both at kind of a high level and maybe a little bit lower level. So let's kind of dive right in, and I'll show you the setup I've got on the workbench here. So I just have the Raspberry Pi and the ADS 1115 analog to digital converter. I just did a little library on this one this week, so there's a new guide out you can check to use this. And basically it takes in an analog signal, which could be anything like from a sensor, or I have a little potentiometer hooked up to it right here that I can change. And it just gives you a digital value, so it'll convert that analog value into a digital value, so like a number. This one's 16-bit, so it goes from like 0 to 65536. Well, actually, it's signed value, so it's like 32,767. But either way, it gives you a digital value that you can use to interpret that analog signal. So if it's like a temperature sensor, you could say, high value probably equates to a higher temperature. And I've got it hooked up to a little logic analyzer, and we'll kind of come back to this in a second. And so I thought it'd be kind of neat to just look at the protocol a little bit. And we'll use this logic analyzer, which basically this is almost like an oscilloscope, but more for reading protocols and digital signals. So it'll sample the I2C communication bus at a pretty high rate, and it'll show you what bit values it sees, whether it's a high or low value. And if I jump real quick to the desktop, I basically got up right here. This is info on the I2C protocol. So it's the integrated circuit communication protocol. It's basically a way for two chips to talk to each other, and it's a serial protocol, which kind of means you have a clock and you have a data line. And there are different serial protocols that the Raspberry Pi can use. So I2C is one of them. There's SPI, which is like a serial protocol. There's just the serial port itself, which can talk to like the kernel as it's booting up. And so I2C is kind of interesting. It's a nice little protocol in that there's only two real wires that you need. There's a clock line and a data line. And just with those two wires, you can have multiple devices, and we'll kind of see how that works in a second when we look at the protocol. Versus something like the SPI protocol, you need a clock line, a data in line, a data out line, a chip select line. And I wouldn't say that one protocol is better than the other. So as we look at I2C, you'll see it has some advantages, but it also has some disadvantages compared to other protocols. So it's kind of neat to just know about all these protocols and kind of know when's kind of the right time to use them. And if you're talking to a chip like an analog to digital converter like this one, you might just have to use I2C, for example. There's some devices that can use multiple protocols. In most cases, for a little sensor, it's going to stick with one protocol. So the Wikipedia page is actually pretty good and gives you a little bit of a description of kind of how it works. But I thought it would be kind of fun for us to take the Celia logic analyzer here, and let's switch to a better view with everything. So let's do maybe this view so you can kind of see the workbench. So Celia is just this little box right here. Really nice little logic analyzer, by the way. You can pick them up in the shop. This is the Pro 8 logic analyzer that I have. It's maybe a little fancier than most people need. So they have a 4-channel analyzer, an 8-channel. This is the Pro version, which samples a little bit faster rate. It uses USB 3.0. And whether you need a logic analyzer is sometimes a good question. So if you're just using chips and talking, connecting devices to a Raspberry Pi, you probably don't need a logic analyzer. If you're working with new hardware and you're maybe writing a library to talk to a device that you haven't used before, then you definitely would have a lot of benefit from a logic analyzer like this one. So definitely think about it. I like it because the software is pretty easy to use. It's cross-platform, and it's relatively inexpensive. I think this one's about $500, but a base kind of 8-channel one is about $200 or so, which in the grand scheme of test equipment is pretty inexpensive, unfortunately. So let's see. So I've got the software set up here, the Celia software, and I have just 2 channels connected. So like I was saying before, the I2C protocol, it just uses 2 main wires, the clock and the data line. There's also power and ground that you usually need to give to a device, but usually you don't count those. So that's exactly the 2 channels I have shown here. So I have the clock channel on the top and the data channel on the bottom here. And the nice thing about Celia software is you can actually add a little analyzer to your protocol, to what you're measuring, and it'll actually decode the I2C protocol for us. So real fast, let me run something on the Raspberry Pi. So I have the Raspberry Pi connected here, and I'm connected to it just with SSH. And I'll run the little ADS 1115 kind of demo program I have on here. And this is just going to read analog values and print them out. So if I run the simple test, and so this is just printing out all 4 channels of this analog to digital converter. Channel 0 is the one I have hooked up to the potentiometer. So when I crank it up, you can see the value increases, and when I turn it down, it decreases, all the way down to pretty much 0. So you can kind of see the full range here. I have the gain kind of tweaked a little bit. So one neat thing about this ADC is that you can change the gain to let you look at a signal that might be at a low level. So my max value here goes from 0 to 3.3 volts, which equals about 26,000 or so here roughly. But that's just kind of showing you the value. So I'm measuring that data, and kind of what's happening behind the scenes is I have a little Python script. It's calling a library that I wrote that's making I2C communication calls to the chip right now. And so I'll use the Celia software here, and I'll just start up the analyzer. I have it sampling for 2 seconds and at a relatively slow rate, because you'll see the clock speed for the I2C communication protocol by default is pretty slow. It's only about 100 kilohertz. So I'm sampling at 2 million samples per second, which means I could pick up about a megahertz signal. So I should definitely be able to pick up this signal. Now I run this and you see, it looks like nothing, but you need to zoom out. So this is showing the full 2 seconds of capture. And so my program every half a second is pulling in a new sample. And so you can kind of see in that 2 seconds I've got 4 samples here. So everything kind of looks good there. Now I can zoom in to these signals and we can kind of see what's going on here with the protocol. So I can go through, and again, like I said before, the top channel here is the clock. And so this is basically the Raspberry Pi is sending a signal that goes high and low at a certain frequency, and then the analog to digital converter is kind of picking that up and understanding, okay, when it goes high, when it goes low, I need to send a bit or receive a bit in certain ways. The data channel is the second one here. And so we'll just kind of dive in and see. So the nice thing about Celia software, you can see it's actually doing some decoding here. So it's telling me that it set up a write of value 144 and it got an ACK bit back. And you can see this little green dot here. So this green dot is actually really important. This is the start bit that tells the I2C bus that something's about to happen, that a device is actually going to send or receive data. Maybe even before we get too far into this digital part of the protocol, one real quick note too on just the physical protocol for I2C. So there are these 2 lines. There are pull-up resistors on these lines that will, by default, if nothing is actually using the bus, these will read at a high signal. And so that's what you see in the logic analyzer here. When the line is up at this higher level here, that means that it's at like 3.3 volts. So it's being pulled up by those pull-up resistors. When a device wants to send a bit, it actually pulls the line down to ground. And so that way, like, multiple devices can be connected to it, and they just have to pull the line down to ground, and they'll be able to send a value, whereas like each device doesn't have to actually push the value up and down. And so that's kind of what you see here, that by default, before nothing happens, we're at a high level. And then to signal the start of an I2C communication transaction, a start bit is sent. And so the way that works is the data line is pulled down, and then the clock line is pulled down after that. So you can kind of see the order here. And that's just a very specific kind of timing thing that has to say, okay, now a device is going to be sent some data. And that's kind of what happens at the start here. And there's also an end bit. So when we get to the end here, you can see this little red dot. And it's kind of the inverse there. So you say, okay, you let the clock line go back up to a high level, and then you let the data line go back up to a high level. So in between here is kind of a whole I2C transaction. And so there are a lot of things that can happen in an I2C transaction. So you can read data, you can write data. One big thing with I2C is because there aren't individual chip select lines, you need to be able to say, okay, I want to talk to this specific device. And if you have multiple devices on the bus, you need some way to identify devices. And so the way I2C works is each device has an address, and it can be like a 7-bit, an 8-bit, or I think even sometimes a 10-bit address. For most cases, it's a 7-bit address like we're dealing with here. And so when like the Raspberry Pi wants to talk to this ADC, it needs to start talking to the I2C bus, and it first needs to send the address of the device that it wants to talk to. And that's what this first write that we see here is, this write of 144 plus the ACK. So you can see if we zoom in a little bit, we'll just look at each of the bits. So the clock line again is at the top here, and you can, if we count like 1, 2, 3, 4, 5, 6, 7, 8. So up to here is the first byte of data, and then there's actually a ninth bit that's clocked out where that's the acknowledgement. So what's happening here is at the very start, the Raspberry Pi, the code that's running on it says, okay, I want to talk to the ADS analog to digital converter. And in the data sheet for that device, you can look up and see kind of what the address is. So the address is a hex value of 48. So it actually needs to send that hex value of the address out to the I2C bus. So it clocks out all of the bits, at least 8 bits of that address. And then the data line is actually going to go high and low to indicate that value. Now the weird thing you might notice, so it's setting up a write, so it's writing a value of 144. And let's actually look at a calculator here, and we'll put 144 in. Unfortunately, Celia software, it seems to only work in decimal. I'd love if it had like a hex mode where it could give me the value of this. But if I have a little calculator here, so we can see decimal value of 144 is equal to 90 in hexadecimal. And so that's a little weird because it's kind of like, okay, I should expect to see a value of 48. But what we actually see here is it's a 7-bit address, and the 8th bit is a value that indicates if this is a read or a write to that device. So what we need to do is actually shift the bits over one place, because that very last bit is telling us if it's a read or a write. If it's a 0, it's a write, and if it's a 1, it's a read. So when we shift it over, now we actually see, if I convert to hexadecimal, it's a value of 48. And so that's what this write of 144 is doing. So it's basically sending the 7 bits of the address OX48 and then a 0 to say, hey, I'm going to write a value to the device here. And then the 9th bit, so let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this bit right here is the acknowledgement, where it's after you clock out a byte of data, the receiving device then can acknowledge that and say, okay, I received that byte. And the way that works in I2C is that the receiving device holds the data line low. So your Raspberry Pi is clocking out the data, and then it waits on that 8th bit, and it actually lets go of the data line. And then your device that you're talking to, this ADS receiver, if it acknowledges that byte, then it actually pulls the data line low. And so we don't really see any change here, but actually what's happening is that the ADS device is pulling that line low, and it's acknowledging it. And so that's why the Celia software here says, okay, we did a write and we received an ACK back. And so that's kind of a nice thing about the I2C protocol, that it's actually letting you know that the device is responding, that you're getting data back. Whereas like the SPI protocol, if you're just blasting out data, you don't really have any acknowledgement. You kind of have to build that into the protocol, so you probably need to read some values back, or maybe have a separate line or something that tells you it's been acknowledged. And then the other cool thing too that we see here about I2C is that it has this concept of addresses, so you can have multiple devices that are all sharing those same lines. Each device doesn't need like a specific chip select line. Just with these clock and data lines, you can have up to 7 bits of devices, so like 128 devices on here. And so that's kind of the first byte that we see is, okay, we're doing a write to this device, and now let's kind of scooch over and see what the next value is. So the Celia decoded it, and you kind of see, the clock is still clocking out data. You can also see here, if I hover over here, and I can't move the mouse cursor, but right above the mouse cursor, it's kind of showing me the length of time. So it's like 5 nanoseconds for this clock low pulse, and then 5 nanoseconds for the clock high pulse. And it's actually telling me that it's running at 100 kilohertz. And so that's another interesting thing about the I2C bus is it's a fixed speed bus. This is in contrast to the SPI bus, where you can control the speed of that as a SPI master. So like the Raspberry Pi, it could run a SPI bus, at multiple megahertz. So if you have like a little LCD display and you want to update it at a fast rate, that's a really good case of using the SPI bus. Versus I2C, by default does 100 kilohertz. There's a high-speed mode where it can do 400 kilohertz. I think there's even faster modes where you can do like a megahertz or more, but most devices that we deal with just run at that default 100 kilohertz rate. And so again, it's a trade-off in that, you know, maybe the protocol is a little simpler, you have less pins you need to deal with, but you don't have control over the speed in a lot of cases like this. But so again, we can see now we're clocking out data. We've got a byte of data here. Now the value the Celia decoded is a value of 1, and then again that last little clock here, here's the ACK bit that's telling us, you know, it was pulled low, so the device responded and said that it received this value of 1. Now the value of 1, you have to go into the data sheet now for the ADS 1115 to understand what it means. This is specifying the register of the device I want to talk to, and a value of 1 is actually the configuration register, and so that's a register on the device that says how the ADC should be configured, like what gain it should use, how many samples it should take per second, and so that's kind of what I'm actually doing here. You saw previously, you know, we told this device we're going to do a write. Now we specified in the next byte the register we want to write to, so this is the config register, and then we're actually sending 2 bytes of data following this to the config register, because all of the registers on this device are 16 bits, so that's 2 bytes of data that we need to see, that we need to send. And so that's exactly what's happening here. So first we're sending a value of 195, we're getting that ACK back, and then we're sending a value of 131, and we're getting an ACK back there. And so that's just sending the configuration. So my Python script has to tell the ADC, you know, what gain, what sample rate it needs to use. It has to flip some bits to say, okay, do a single shot capture. But that's kind of the first transaction here that we can see. You know, we're doing a write to this device. We're specifying the register, and then we're specifying the value we want to write to that. So there's basically 3 bytes of data that we're writing to this device. Now if we go over more, and you'll see kind of this big delay in between the different sends of the different kind of transactions, and that's really just the Python code on the Raspberry Pi. It's maybe not that big. I mean, 8 milliseconds, that's pretty small, but you can see in the grand scheme of things, like compared to how fast the actual bits on the bus get clocked out, you know, this is pretty long, and that's just my Python program. You know, it's doing other processing in between here, and you can kind of see how, you know, if you compare this to like maybe an Arduino, for example, that's not running a full-blown operating system, you know, there could be a lot less delay between different I2C transactions because there's less stuff that you might be doing in between here. But let's take a look at the next transaction here. So we'll kind of zoom in and see, okay, so this next one, again, it starts with a start bit. So, you know, we pull the data line low and then the clock line low. And again, we're writing a value 144 and getting an ACK back. So that's the device address. So that's a hex value of 48 once we do the conversions and drop that last bit. Also interesting to see, this is another write that we're doing here. So now we're basically saying, oops, let me scroll over here. So we're doing a write and we're doing a value of 0, and then this little red circle is telling us now we're sending a stop bit. So we're basically just sending 1 byte of data here. So we're telling the device, here's the register that we're going to read from next. And this comes down to the protocol that the device wants to understand. So, you know, to talk to this ADC, to pull a value from it, you first have to write a byte that says, okay, now switch to the actual ADC output, which is register 0. And then we're going to do some reads after this. And so now we can see another I2C transaction starts right after this one. So that's where this little green circle is again. And in this case, it's a little bit different. So we can see the very first thing we do is we're writing a value of 145 instead of 144 like we saw over here. And we're getting the ACK back. And so let's just kind of decode that. And you'll probably see pretty quickly kind of what the difference is. So, you know, if I put 145 here, now we can see, okay, if I shift this over one place, we get a hex value of 48 again. So we're talking to that device that has address 48. But if I go back and I put 145 in, we can see that 8th bit is a value of 1. And so that's that read-write bit. And so now that bit is set to 1. And so this I2C transaction is a read. And so that way the device, the ADC, knows that, okay, hey, the Raspberry Pi is talking to me, but now it's going to do a read. And so it actually looks to see, okay, what was the register that was previously set in this previous write command? and then it's actually going to send out the value of that register. And so now you can see that we clock out another 2 bytes in the clock here, but it's not the Raspberry Pi that's actually changing the data line here. And unfortunately, you can't really tell which device is pulling the line low, just kind of an artifact of just having these 2 lines. But you can see that it's getting a value back. It's getting U, which actually this is it's converting the value to ASCII. So it's just a little bit of a weird kind of quirk of how Celia software works. But it's getting one value and then it's getting another value, and we're ACKing that value again. So like, let's kind of zoom in on the value we're getting back. So like, we're getting back a value of U. So, and let's actually look at this hex value here. So like, let's see, this is let's see if it tells us the actual raw value. It doesn't really tell us the raw value. That's kind of nice, so we can zoom in there. So okay, this is giving us a value back. The very last bit is again that ACK, and because it's the device talking to the Raspberry Pi, now it's the Raspberry Pi that's actually pulling the line low here. So this ACK goes kind of both ways here. And then the next bit, the next byte that it reads, it gets a value of 215 here. And you see a NAC value, and unfortunately the software kind of goes crazy when I put the mouse over it, but there's a difference between an ACK and a NAC. So in this case, the ACK is the Raspberry Pi telling the device, okay, yes, I received that byte. Now, and it does that by holding the data line low for that final 9th clock kind of cycle. A NAC bit is the opposite, when the device actually holds the line or lets the line go high again. And so we actually see in this last clock cycle it's high, and that's sending a NAC, which is like a negative acknowledgement. So this is actually the Raspberry Pi telling the device, okay, I read that second byte and I'm done reading bytes. Like, don't send any more bytes of data, or don't expect any more bytes of data to be sent here. So it's a little subtle difference, but it's kind of a way for the master that initiated the communication to say, okay, I only want to read 2 bytes of data. So it reads 1 byte, sends the ACK, reads the second byte, and then sends a negative ACK or a NAC to say, okay, I don't want to read that data anymore. And then it sends the I2C stop bit again here, where it says, okay, now we're going to let the clock line go high and then the data line go high after that to acknowledge the end of that. So what's happening here in this in these 2 transactions is we're reading the ADC value. So to do that, we first do a write to say, here's the register I'm going to read, and then we do a read of 2 bytes because it's a 16-bit register, and we pull down those 2 bytes of data. And then my program can kind of interpret that raw value to say, okay, I need to do 2's complement conversion on this, and basically turn it into a signed integer value. And that's what we see when it's printed out here. So as I change the potentiometer, this value changes, and it's getting back a different value from that register that it's reading here. And so that's kind of all you see for the rest of this program. So here it's doing a write to the config register again. Basically every time it does a read, it's doing a config write to say, okay, I'm going to start a single shot read again. And so that's kind of at the low level what we're seeing going on here. So it's it's interesting just to be able to look at that kind of wire protocol here and see the raw things that are happening. I think what I'll do now is maybe we'll jump in and we'll look at the actual code that's making this work on the Raspberry Pi. And so let's jump back to the Pi, and I have over here some code that I wrote earlier. And maybe we'll kind of dive into this. So there are 2 things I'll show as far as how to talk the I2C protocol from Python with the Raspberry Pi. I'll show kind of a high-level way to talk the I2C protocol that uses a library called the smbus library, and then I'll show a lower-level thing, something I'm kind of working on now, that's actually just using the raw kind of Linux device that's exposed for the I2C communication bus. And maybe before I dive too much into the code, I think I'd shown this before, but there are some interesting tools in Linux that let you look at the I2C bus and kind of see what devices are there, because we saw earlier it's a bus where each device has an address assigned to it, and it turns out there are kind of some neat ways that you can query the entire bus to see how many devices and what devices are there. So if you install the I2C-tools package, this I2C-tools, you just need to apt-get install that. There's a program called I2C Detect. You need to run it as root. So we'll say I2C Detect. We give it the -y option because normally it asks, are you sure you want to scan the bus? And yeah, I do want to scan the bus. And you have to specify the bus number. And we'll look at this in a second. But I can run this command, and it's actually scanning the entire I2C bus. The way that scanning works, from what I understand, is it actually it sends out a command, kind of like we saw here, that says, hey, I'm going to do a write. It sets up a write to every single possible I2C bus, and it looks to see if it gets an ACK bit back. So it looks to see if some device holds the data line low, and if it sees that, then it knows, okay, there must be a device listening on that address. And so that's kind of how that tool works behind the scenes. But it's telling us, here's the device with address 48, just like we saw kind of from the raw protocol and the code that's running there too. The actual I2C bus in Linux, so it's exposed under this I2C dash some number. So on the Raspberry Pi, there's just one I2C bus that we can talk to. So it's this I2C-1. And so that 1 is kind of the bus number. To get this, so if you just have a fresh Raspberry Pi image, you do need to be careful. You need to run the Raspberry config tool and enable I2C. So I won't go through it all, but I'll just kind of show you. This is a super common thing that people miss where you're talking to a library that uses I2C. If you forget to enable this, so it's in the advanced options, you go under I2C and you want to enable it. I'm just going to cancel out of this. But if you forget to do this, then you won't see any of these I2C devices. You'll just get nothing if you try to query them. So enable the bus, restart the Pi, and then you'll actually see these I2C devices. So there's this device under the dev node that gives you this I2C interface. Now the code to actually talk to this thing, there's a Python library called smbus, and smbus is actually a subset, from what I understand, of I2C. So I think there were like devices on motherboards, things like temperature monitors, actually use I2C protocol, but they use this subset called smbus that basically doesn't have all the capabilities. It uses the same kind of protocol like we saw, there's a clock line, data line, but it's more register focused. So it's talking to devices that have a register that it wants to read a value from or write a value to. With I2C, you actually could just write like a raw single byte if you want, but this smbus protocol is more to deal with like devices that have registers. The difference really doesn't matter much. Most cases, a lot of devices that we use are register based, and so we can use the smbus kind of libraries and protocol. But there are some devices, like I was actually just dealing with a little humidity sensor, the SHT31, that doesn't use registers. And so we'll kind of look at that at the end here when I look at the kind of raw way to interact with I2C devices. But it's just something to be aware of, that you might see smbus, and whenever you see that, you really just need to think, okay, that's I2C, but a little subset of I2C. Now the main library that everyone uses is this library called Python-smbus, and it's actually part of that I2C tools package. So when I apt-get install I2C tools, it's actually the Python library is a part of this. Now in Raspbian, to actually install this library, you really want to install the Python-smbus apt-get package. And so this package will install the smbus library for the version of Python on the Raspberry Pi. And I wanted to kind of figure out and see, where is this library? Like, let's kind of look at the code for it. And it's kind of an interesting thing. So when you search for it, it's actually this lmsensors.org, and unfortunately it looks like their website is down. So we'll just go to the Internet Archive, and this must be a temporary thing. But it kind of tells you about, this is a little thing for kind of Linux hardware monitoring. And they have their code. It's in a Subversion repository. I did a search, and actually someone mirrored it on GitHub, and so it's a little bit easier, I think, sometimes to look at a GitHub repository. But this is basically a mirror of that code. And you can actually see, here's the PySmbus folder, and here is the actual implementation of that Python smbus library. And I mention all of this because, unfortunately, the documentation for this library is not the best in the world. So I guess, yeah, there is some documentation here, and let's see if they actually show the Python docs. Because it's one frustrating thing. I see a lot of people, you might be coming from like, maybe a Windows world or something where a lot of libraries are documented really well, and you kind of start playing with Raspberry Pi and I2C, and it's like, okay, where are the docs on this thing? And unfortunately, yeah, I really couldn't find good docs on the I2C Python library. So if they're out there, maybe post in the comments or something of this video later. I'd love to see what's out there, but unfortunately that kind of means the best documentation is the code here. And so the code for this it's a Python C extension, which is pretty advanced. If you're new to Python, this is going to be pretty confusing, unfortunately. So this is C code that exposes a Python class, and I won't get too deep into this. Just the interesting thing is if you kind of browse through this code, you'll see all of the functions that it exposes, like this read word data. This is how it's implemented in the C code here. And so really, this library is just a wrapper around a library that Linux provides you already. So like this read word data function, this is exposed as a Python function. You can't really tell the parameters it sees here. This is just the way Python C extensions work. You have to actually parse out the parameters because everything is dynamic in Python. In C, it's not dynamic, and so that's where you kind of do that conversion in your C extension. So we're saying that, I need to read two integers here, this II, and so it's going to parse out the address and the command. But all it's really doing is actually just calling this I2C smbus read word data function. And this is a C function. It's provided in a library that's installed on your Linux operating system. And so that's all that this Python library is. It's really just a thin wrapper around that C library. And so that's maybe where you want to start when you want to look at documentation for how to use the Python smbus library. Look at this page. This is from kernel.org, which is kind of the homepage of the Linux kernel. And it's the documentation for the smbus protocol. And so this actually goes through and says, okay, these are the C functions that the kernel kind of user interface exposes. And so we can see, like, here's an I2C smbus read byte function. Here's smbus read word data function, which, as we just saw in the Python library, here's the read word data function. So it's calling this function, which is actually here. And now we can actually see a little bit more useful documentation. And it's telling us, okay, this operation, it's like read byte, but it reads 2 bytes of data because a word is 2 bytes on these systems. And the really cool thing about these docs is that it actually tells you this is what it's going to do over the wire with the I2C protocol. So, and back at the top, it tells you the keys here. So, it's going to start with a start byte. So if we look back at the read word data, so this S is telling me, hey, I'm going to send a start bit. Then I'm going to send the address. Then I'm going to send a bit that says this is a write. And then it's going to wait for an acknowledgement. Then it's actually going to send a byte that says, okay, here's the register I want to talk to. And then it's going to wait for an acknowledgement. And then it's going to send another start bit. And then it's going to say, okay, here's the device address. Now I'm going to do a read, wait for the acknowledgement, and then read my 2 bytes of data with an acknowledgement and a negative acknowledgement, a NAC at the end. And then the P is the end bit. So that was exactly what we saw with our low-level communication here from the Celia. So we saw that start bit, we saw it doing a write with the register, and then we saw it doing a read and the 2 bytes of data coming back. And so that's one really nice thing about the documentation for this, is that it's maybe a little scarce and hard to track down, but at least kind of tells you here's exactly what's happening here. And so based on that, you can kind of know, okay, when I look at my datasheet for my device, it's telling me to read the ADC value. I need to do like a write to the register, and then I need to do a read of 2 bytes. And so I can go back and see, okay, I really want to call this smbus read word data function. And so that we kind of bubble back up to Python then. So this Python code is just a real light wrapper around that kernel functionality. And so now if I jump back to, I made a really simple Python example here that's using that smbus library. So I'm just importing the library. I have a little bit of configuration at the top here to say, okay, which bus I want to talk to. So, like we saw before, there's that I2C-1. Some devices have multiple I2C buses. So like the BeagleBone Black, for example, has bus 0 and 1. So just something to be aware of. You might have multiple buses. So we specify the bus. We specify the address, so that OX48 that we saw. Now to use this library, you basically create an instance of the bus. So you pass in the bus number you want to talk to. And then I do a read word data call. So like we just looked at before, I pass the address of the device I want to talk to. So what I set up here, that OX48. And then the value, I want to read from the register OX01, which is the config register for this ADC. And then I just do an AND by FFFF. This is just with Python, like I've kind of said before. All of the numeric values in Python are signed 64-bit integers. And so when I want to deal with a smaller type, I want to just do a Boolean AND to say, okay, I only care about the lower 16 bits of that data. So FFFFF is basically 16 bits that are all set to 1. So we're just pulling out the 16-bit response. I technically don't even really need it here. It's just I get in the habit when I'm writing code in Python that's talking to devices and doing embedded stuff. I like to be very explicit and say, okay, I'm expecting to get back a 16-bit value, so those are the only 16 bits I'm going to talk to or care about. I'm just going to mask out everything else. And it's smart to do that because you might forget to do this, and then maybe you actually are reading data you don't expect, and you're getting maybe higher than a 16-bit value, and things just start subtly breaking. So you see this a lot in my code, and that's just because this is effectively converting to a 16-bit value. As a side tangent, something I want to do some days, I want to sit down and write a little library for Python that's like an embedded helper, because there's no reason that Python can't have smaller data types like a 16-bit integer, an 8-bit integer. You can actually see, and one really useful thing if you're maybe wanting to go from beginner to more intermediate and advanced Python programmer, start reading the source code to Python. You can find it online, and it's actually installed. I think it's in the site packages folder. Yeah, what the heck? Let's take a look and see if we can find it. So if I go on my Raspberry Pi, I should be able to go up a value. Actually, here, let's go to, I don't want to go to the home folder. Yeah, I think, let's see, it's under, where do they put this stuff? I think it's lib. No, maybe it's not there. Oh, I think it's under the user. Yeah, let's see, user lib, maybe Python 2.7. Yeah. And so this is actually where you start to see all of the source code to Python, because most of Python is written in Python, and everything that's not written in Python is just C. And so if you dig deep into this, I forget exactly where it's at, but you can actually see where they implement the numeric type in Python, and it's kind of fascinating. But anyways, to come back to the tangent, so I think it'd be cool someday to sit down and write a Python type that's, like I want food to be, a uint 16 or something like that, that would actually do all of this masking and stuff for you. So something for a rainy day. But anyways, coming back to this. So this code, I'm calling that read word data function. I'm getting the value back, and I'm just going to print it out. So let's actually run this code. It's a couple directories up. So we'll call the Pseudo Python I2C read.py. And so it's going to read the value of the config register, and then it's also going to read the raw ADC value and print that out here too. So that's what the rest of this code is doing. So I'm actually, after I read that data, I'm doing a write. So I'm going to call write word data, and we can go back and we can see the kernel functions again. So let's look at like write word data. This is probably, yeah, here we go, write word data. So this is going to do an I2C write and of 2 bytes of data, so a word of data. And here I'm basically just setting the config register to explicit bit values that I want. This just comes back to the datasheet for the device. So when I want to configure it to do a single shot read, I need to send some bits that look like this. So I call this write word data. I pass it the address of the device again. I pass it the register I want to talk to, register 1, which is the config register. And then I pass it the 16 bits of data that I want it to set to that register. And so that's what it's doing here. It's going to make an I2C write for this register for that data. And then right after that, I do a read again. And this time I read from register 0, which on this device is the actual ADC value. So after I write the config, I do a read, and then I just I do a little bit of bit manipulation. So this is another thing I don't like about the smbus library. Because it has a concept of reading words, which are 2 bytes, suddenly you have to deal with Endianness, and the Endianness is kind of the byte order. So, a 16-bit value has 2 bytes, and so there's a low byte and a high byte, and it just comes down to how the data is packed. So you could put like the most significant bits, these are the highest order bits that control the value the most. You could put that first, and then you could put the low order bits after that, and that's big endian. Or it could be little endian, where you have the low order byte first, and then the high order byte, the most significant bits after that, and that's little endian. And it comes down to what processor you're running on and what endianness it expects, and it can change if you're running on a different processor. The Raspberry Pi, for all of your user code like this, is little endian. So your least significant byte is first, and your most significant byte is after that. Unfortunately, a lot of devices you talk to, like this ADC, are big endian, so they send their most significant byte first, and then their least significant byte after that. And so that's what I'm doing here, is I'm actually swapping the byte order to say, okay, now, because I'm running on a little endian device and it's talking to a big endian device, I need to actually explicitly flip those bits. Now, if I just talk to the device at a byte level and I ignore like sending words of data and things like that, then I don't really have to care so much about the endian order. I mean, if I want to look at a 16-bit value, I still have to take those 2 bytes and put them together in some way, and so I do need to know the endianness there. But it's just something to be aware of and to be very careful about. When you start dealing with more than 1 byte of data, you do have to think about what's the endianness of the devices you're talking to. And you'll usually see pretty quickly, if you get it wrong, that like your values are way out of whack, and they're super high when they should be low, and vice versa. But that's all I do here, is I just do that conversion and then print out the raw value here, so we can kind of see that it was giving me a raw ADC value of 12A8 here. And so that's really all there is to using that smbus library. I mean, it's not that hard as far as, there's not a lot of setup you need to do. You just create an instance of the bus and just call read and write functions on it. So there's read word, write word, like we saw here. There's read byte, write byte. You can read a list, so there's like these block data function calls, and so you can read a whole list of data here. And so that's good to be aware of that. That's kind of the high level interface for this. And then I have a little wrapper that I put around this, and it's in our kind of Python GPIO library. And so all of the libraries that we publish with Python code, they use my little wrapper here. And this was mostly just to hide platform differences. So like I try to detect what bus you're using, so that you don't always have to explicitly say, I need to use bus 1. So like on the Raspberry Pi, I can assume that bus 1 is kind of the default, and actually it changed. Like very early revisions of the Pi had the I2C Bus 0, so it's weird little things I can kind of smooth out there. Like on the BeagleBone Black, it has multiple I2C device buses, so I pick one and say, okay, I'll default to bus 1. But I basically just have a light wrapper around all this. So, I have all these functions here, like I want to read, read U8, so read an unsigned 8-bit value. And right here, I'm actually just using the smbus library. I'm calling that read byte of data. But I put in these nicer, higher level functions, like if I want to read a signed 8-bit value, I'll do the read, and then I'll actually do the conversion from an unsigned to a signed value. So I'll kind of smooth over some of the issues that you might run into here. But at the end of the day, I'm just using that same smbus library. So you can see I'm importing it and just using it here. I've just added extra functions to it. So something I wanted to dive into a little bit deeper then is, okay, so what is the smbus library actually doing? Like we saw here, it's calling these Linux functions that are making these I2C smbus reads and writes, but there's actually something another level deeper that we can look at, and it's really the raw device here, this dev I2C 0 bus or 1 bus. So this is a device in the Linux file system here. You can actually open this and you can read and write bytes to it like you were reading and writing to a file. And Linux will actually interpret that as sending and receiving data over the I2C bus. And it will actually make I2C protocol commands and calls for you, just based on that. And you can see documentation for this. So again, if you go to kernel.org and you look up the I2C dev interface here, and maybe when this video goes up on YouTube, I'll put in the description just direct links to this so you can look and see. But this is a really good little piece of documentation to check out. And just in general, all of the documentation from kernel.org, from the Linux kernel, is super useful to read. It assumes a little bit of knowledge about Linux, so for a very beginner it might be kind of hard to read. But as soon as you start wondering like how do these things work, go straight to the kernel.org docs because they're pretty high quality. And so this actually tells us about this I2C device. So it tells us it's a character device that you can read and write data to. You can open it just like a file. They give sample code here that's using the open function. This is C code, and it's you can do reads and writes here. Now the interesting thing is, like we saw, the I2C protocol is not it's more transaction based, so it's not so much of like I'm just going to write some data and read some data. Like I might need to write a register and then read a few bytes of data from that register, and so that doesn't fit super well with Linux's kind of character device functionality. There is no like transaction where you can do a read and write at the same time or things like that. And so the way they work around that is this I/O control function. And I/O control is kind of a way to talk to a device driver at a lower level. It's almost like calling a custom function. So a device driver, like the I2C driver, can say, okay, I'm going to expose a character device you can read and write to, but I'm also going to expose some extra functions that you might want to call. And you do that using this I/O control function. And I won't go too deep in the details here, but using this, you can actually do things like construct an I2C transaction that says, okay, I want to write a byte of data, and then I want to read a few bytes of data back. And so there's this I/O control function where you pass it a special read-write value, and then you have to pass it a structure that you construct that says, here are the individual calls that I want to make in this transaction. And they go through and they give a little bit of C code. There was actually some good code that I saw. Let's see, Sean Cross, I2C device read. So let's see if I can find this. Yeah, here we go. This is an example for tickling the I2C bus. So this is a really good example from Sean Cross where it really just shows using the raw I2C device and using that I/O control function. And this is C code, and so it's showing you how to construct, a couple messages, like I want to do a write and a read and pull back data. And so this is good to start looking at, okay, how to talk to these I2C devices at a lower level. And what I did is you can actually convert this code into Python code. And so Python has some libraries that let you interoperate with C functions. And so I did that actually as an interesting example that we'll look at here. So Python actually gives you that I/O control function. So I can call that from Python code. Now the C structures that I need to build up, you'll see some ugly code here, and things get a little crazy because to interoperate with C code in Python, you have to use a library called C types. And C types, it's actually included in Python. It's a pretty core part of Python because a lot of Python is just talking to C functions. And so this lets you actually construct parts of memory that are compatible with C libraries and C code. So in my Python code, I can actually construct a bit of memory that has the same format as the C structure that the I/O control function expects. And so that's what I actually did here in some Python code. And maybe I won't get super deep into it because C types in general is really complex, because the problem is like Python is a dynamic language that doesn't care about types. C is all about types and strict type checking and things, so you have to bridge that gap using C types, and so things get ugly. Like I have to actually explicitly define these I2C structures, which the kernel defines, and you can see in the documentation here, like this I2C read-write I/O control data struct. I basically have to redefine that here. And so this is made up. There are two fields. There's one field called messages that's a pointer to another structure. It's actually an array of structures. And so this structure has like the address, the flags, what data you want to send. So this gets a little crazy, but it's not, once you understand C types and you are a little more familiar with Python and C code, it doesn't look that crazy as far as, you're just mapping the C definition to a Python definition here. So once I have those structures defined though, then I can actually go in and make that IO control function call. So all the way down at the bottom I do that, but before I get there I actually have to construct some data that I'm going to send to it. And so that's what I do here. So first I actually open up that dev I2C device. I read it, I open it for reading and writing as a binary object. And so once I have that open, then I need to construct these two messages that I want to send it. So I basically need to first send a write that says this is the register that I'm going to read from. And so I send it a message. So in this message I say the address of the device I want to talk to, so that OX48 like we saw. Flags, this just says what kind of operation this is, and so there are explicit values that I pulled out of the headers from the Linux kernel that tell you kind of what these values are. And so you can say, okay, I need to do, there's a read operation type. You can also specify like if I have a 10-bit address instead of a 7-bit address. Lots of little ways to tweak the behavior. By default, the value of 0 is going to do a write. And then the second message, I'm actually going to do a read, and so I send it a different flag value here. But after I set the flag, I then need to set the data that I'm going to send in this write. And so I'm going to send 1 byte. Now I have to send it as an array or a buffer, and so I need to construct that first. I actually need to use the C-types library to create an unsigned integer 8-bit value. And I have to do this because, C-types is letting you interoperate with C code. There's no guarantee in Python that your number is an 8-bit value. So by creating this uint8, I'm basically telling C-types, go make a bit of memory that is an unsigned 8-bit value and give it a value of 0. And then I basically have to send a pointer to that value, and this pointer is like a C-types function that gives you a pointer to another C-types value. So all of this ugly code is basically just emulating the C code that we see here. So I'm basically saying, okay, I need to set the address, set the flags to 0, and then actually send it a value that I've set before, so this input buffer of data that it has. So I send one message that's going to write the register, the register that I want to read from, and then I construct another message. This one's going to be a read, and here I'm actually going to read 2 bytes of data, and I actually need to create a buffer in memory of 2 bytes, and that's what this does. And then I need to set that in my message struct, and you have to do some funky casting here. If you've ever used C-types much, it's ugly, and it's just, again, unfortunately, how to convert between kind of the Python world and the C world. There are better libraries, by the way. If you do a lot of C interop, there's a library called CFFI, C Foreign Function Interface, and that is a really nice library. Unfortunately, it's not included with Python. You have to install it, but you can actually just copy and paste your C header that defines all your functions and your structs into a string, send it into that library, and it will do all of this junk for you. So, I'm actually doing this the hard way because ultimately I want to write a pure Python library to talk the I2C protocol. Because one big thing I kind of forgot to mention, that Python smbus library only works with Python 2, unfortunately. So it's owned by that I2C tools package, this LM sensors library. For whatever reason, as far as I can tell, they don't have a Python 3 version of it. And one unfortunate thing, in Python 3, they changed the format of C extensions. So this thing doesn't work anymore, which is a problem for us, unfortunately, because all of our libraries are written to use Python smbus. And so that's kind of what made me start looking at things at a lower level, is to see, okay, how can I make I2C stuff work in Python 3? And I think a smart way to do it, it's not necessarily the best way, but a smart way to do it is to write pure Python code where there's no C extension. It's just Python, and pure in the sense that I'm not relying on any libraries. I'm just using built-in Python stuff. So the C-types library is built in, IO control is built in. That's all I need to talk I2C. And so when I do that, then I can actually make this work with Python 3, because Python 3 also has the IO control library function. It also has C-types built into it. There's sometimes little differences in those libraries, but you can kind of smooth those over in your Python code. I'm not actually building a C extension. And the nice thing is, because I'm not building a C extension, you don't need to have the Python developer tools installed, like all the headers. You don't need to have the C compiler installed. You can just do a pip install that's doesn't depend on anything really for your library. Now, I said that this is not necessarily the best way because there is a little bit of overhead when I'm doing this. So, you can see all this code I'm doing, like I'm creating bits of memory to hold like a byte of data. I'm creating, 2 bytes of data as a buffer. That's overhead. Like, it takes time. Python has to do this. It's going to call some functions to allocate this memory versus this C code here. This memory might have been allocated on the stack, and so it's just there as soon as the program runs. There's a lot less overhead here. So it's going to be a little bit slower, and I think that's an okay trade-off. So, it's like the classic like speed versus kind of functionality trade-off. In my case, for all these libraries we publish, we want them to be easy to use. So like if you don't have to compile a C extension, if you can use it with Python 3, that's a big win. Speed is not necessarily our highest priority for these, especially for stuff like I2C, because you saw the bus runs at 100 kilohertz. With a gigahertz processor, you're going to fly through a lot of operations in the time it takes for the I2C bus to return some data. So even though there is a little bit of overhead here, I think in the grand scheme of things it's okay. And the famous quote, "Premature optimization is the root of all evil," that always holds true. So your first inclination might be, this is not going to work, I need the fastest stuff possible. But try it first. Try the simple way, maybe the easier to kind of maintain way, and in most cases it's probably going to work. And there definitely are cases where it's not going to work. You might be in a tight loop where you're reading data constantly, and in that case, go optimize that path. Like, maybe go into that loop and don't use this library. Write a C function, and Python makes it really easy to talk to C functions, and so call your C function there that's faster and more optimized. But in this case anyway, so coming back to this, that's why I'm looking at the I2C protocol at such a low level here, because I think it would be interesting to have a little library that actually just talks this low level kind of Linux I2C protocol. So anyways, coming back to what we were talking about before, ultimately we've got the 2 messages we constructed. Now I just need to build this IO control kind of transaction that just has those 2 messages, and so then I make that IO control call right here, and so I have to pass in the file descriptor for this file that was opened here. I pass it the IO control function call I want to make, and this is actually just a hex value, so it's let's see, this is this 0707, and so the device driver for I2C will then interpret that as it's going to do a transaction of multiple messages, and I'm passing in this request that has these messages that I built. So once this call happens, it's going to unpack this array of messages and say, okay, I need to do a write with 1 byte of data, and then I need to do a read with 2 bytes, read 2 bytes of data and return them back. And the way the data is actually returned, this buffer that I pass in right here, this kind of result type, this will actually be set with the value that was read here. So let's run this function. Let's run this example. Let's run this raw I2C read. And you can see it gives me back a value, so OX2097. Now let's go back and let's run my read value here. So this was the previous example. So this is the smbus example, and you can see it's returning the raw I2C value of 2097. And then that raw I2C read, this is the kind of raw IO control version, and it's returning the same value. So that's good. Like, that's kind of telling us, hey, we did the right thing here. And it's kind of showing us that you can make these low-level IO control function calls even from like pure Python here, and you can get data back that kind of matches the data that you expect here. So like I was saying before, this is kind of the low level. Most people don't need to get this low of detail, but it's good to know that you can. Like I was saying before, that this smbus library, it deals with like words and bytes, and everything has to have a register in most cases to write to, and not every I2C device deals with that protocol. Not every I2C device is an smbus device, for example. So if you do have a device where it doesn't deal with registers, for example, you might need to drop down a little bit lower and do things like these IO control calls, or you can actually just read and write bytes of data to this I2C device. But again, it's, not something, I wouldn't jump to this first. When you're talking to an I2C device, try and use the higher level abstractions like the smbus library, and then once you run into a roadblock with that, then go a little bit lower, because as you can see in the difference in code here, like there's a lot of stuff going on. There's a lot of boilerplate, a lot of things to get wrong. And one big thing too, when you're interoperating with C code, you don't have a lot of the protections as you do in Python. So, if you get the length of your buffer wrong, it will happily overflow memory, and you could seg fault and have all kinds of fun stuff exploding on you. So it's not fun, but it is possible, and you can definitely do this kind of interop in Python. So I think that's all I wanted to cover as far as like a bit of a super deep dive, maybe just to kind of summarize. So talk a little bit about like what I2C is. The Wikipedia page is all right. It's a little long, but you can kind of Google around and search and see. It's just a serial protocol for two chips to talk to each other, and it has some advantages and disadvantages compared to other serial protocols. We looked at on the actual wire, like what's happening with an example of an I2C device. So using the little Celia logic analyzer, you can see the I2C transactions and the start bits and stop bits and the clock and the data. And we kind of talked a little bit about the addresses and the different types of transactions you can do, like reads and writes. And then we kind of dove into how to talk to this stuff from Python using that smbus library, here, and like here's the GitHub code for it. And so this is, mostly the high-level interface that most people are going to want to use. And then we looked at the low-level stuff of like, okay, what does the actual Linux kernel expose to talk to these I2C devices, and how can you even talk to that from Python? And so you can see just using that IO control and the C-types library, it is possible to do that. I guess if anyone has any questions or anything, I don't see a lot of questions in the chat right now, but maybe fire them off, and I'm happy to answer them. But yeah, I hope this is a good kind of overview of I2C and how you might use it in Python. It's kind of interesting, I think, too, just to look at all the different kind of protocols at a low level and kind of see what's happening here. I mentioned at the start the SPY protocol. So the Linux kernel does have a low-level interface to that. So let's see, we'll search like Linux SPY dev. And so, yeah, again on kernel.org. So this tells you all about how to talk to a SPY device, and maybe a future video I could go in and get a little more deeper dive into that one. But just like I2C, it's got the same thing with IO control, and you can read and write characters and things like that. So it's sometimes interesting to go down to that lower level. I don't see a lot of questions, so I think that's probably it. We'll wrap it up, and that was the deep dive with Python and the Raspberry Pi. So thanks a lot for watching. Subscribe to youtube.com/Adafruit, and you'll see a lot of cool projects and things. Subscribe to twitch.tv/Adafruit, and you'll see I usually stream to Twitch, and keep kind of up to date on what's going on. Definitely check out the Twitch channel and the YouTube channel. You'll probably see some more from Lady Ada. She's streaming a lot this month for the Raspberry Pi Zero contest. So if you haven't seen it, go to the Hackaday Zero contest. So with the Raspberry Pi Zero, there's a contest going on. If you come up with an idea for a fun project, you might be able to win a Raspberry Pi Zero. And then if you build a fun project also, there's some cool prizes you can get for that. So check it out. Thanks a lot for watching, and I guess I'll see people probably in a week. We'll do another stream on some stuff.